Here again, we're given diagram, and here the weight is 1,000 pounds that we have to contend with. All right, so what are all the things we're asked to find in this problem? Right, so the three cables here, the AD will be pretty straightforward, but the 1 bar and 3 cables. So for the bar, I'm going to call that FAO. We want TAB, TAC, and we will need TAD, but that one's going to be pretty trivial since all it does is hold that weight. We are given a coordinate system, so again, I'm going to stick with that Z up, Y right, X forward. So what's our particle of interest? Again, it's trivial for this, but it will get more complicated. A is what we want to pick. It's attached to both ropes, the rod, and that weight, which in turn is attached to another rope. So A is going to be our particle of interest again in this one. So take a moment and make the free body diagram. I'll kind of draw it as we go in the interest of time. But A is first of all, and we want to include all of the coordinates. So for the skeleton of the free body diagram, since we have forces that are going to point from A towards the origin, towards B, and towards C, these points I want to make sure I include right away. As far as the forces go, the easy one is going to be that vertical force down of 1,000 pounds. And that we know is going to be equal to the tension in AD. Because that rope just holds that weight, the tension in that rope is just going to be the weight force. So we don't have to go through extra steps here when it's very easy like that. TAD right away we know is 1,000. The others are not going to be so easy. So as before, we saw these 3 unknown tensions attached to it. Yeah? FAD? This is TAD.
No.
FAO.
Oh, okay. Sorry.
So 3 unknown tensions. Again, we know where their directions are. It goes from A to C, a tension from A to B, and some force from A to O. So just like I did in the last one, I want to direct my forces along those directions, and I'm going to assume tension, which 2 of them must be. Right, so 3 unknown forces, or at least unknown magnitudes, but we know that they point A to C, A to B, A to O. Right, questions on the free body diagram for this. Not all too different from the previous one. So we don't have as easy a time here as in the previous example because all 3 forces are in multiple coordinate directions. So none are just along X, Y, or Z. So that means we do have to go through the full steps to find the unit vector for each of these. So I'll go through in detail the first one, and then I'll just write the other 2, since it'll be the same process, just so you can see this again. So a unit vector that points from A to B, which is also the direction that TAB lies on. So position vector AB is going to be B minus A in the numerator. 15 minus 15 is 0i. 0 minus 48 is minus 48j. And 36 minus 0 is plus 36K. This one does have a nice round magnitude. 48 squared plus 36 squared is 3,600. So the magnitude, we get a nice round 60. So we can represent this as a fraction. So in the interest of time, I'll leave it as an exercise for you. For U hat AC, we're going to get negative 5/13 I plus 12/13 J, 12/13 K. And for U hat AO, we don't get nice fractions. We do have to go to decimals. Again, 3 digits is sufficient for this. Negative 0.299 I minus 0.954 J. Write our equilibrium equations. So remember what we were looking at is that we can express, I'll use as an example here, vector TAC, we don't know its magnitude yet, but since we know its direction, we can say it's negative 5/13 magnitude TACI plus 12/13 magnitude TAC K. So we get to this step writing our equilibrium equations, we're just picking out, for example, in the x direction, we just want the coefficient in front of what would be the I, J, or K term, depending on which equation we're looking at. I'm not going to be writing this each time. You can initially while you're kind of working on this, but I'm going to skip over this step. It's kind of implied to what we do in the next step. All right, so with that in mind, what is our equilibrium equation in the x direction for this problem? Yeah.
Negative 5/13 TAC minus negative 0.299 FAO.
Right, and that's it, because AB does not have an I component, and W does not have an I component either. So 0.299, and right, times that force FAO that we talked about on Wednesday. So this is the whole equation. We have two unknowns. We have one equation. Right, so that's all we can do with this one. We can't solve for a number yet, so I'll add more equations and then kind of revisit it as we go. So in the y direction, what are the forces in the y?
Negative 0.15 for the TAO.
FAO, I called it. Right. It could be it could be tension or compression. I call it FAO, but right. What else is in this equation?
Minus 4/5 TAB.
TAB, correct. So we have three unknowns, two equations. So still numerically, we can't solve anything yet. So we can add, since we're in 3D, a third equation in the z direction. All right, so what do we have in the z direction then?
12 left of the TAC.
Where is that? Right, so here, 12/13 TAC. Yeah,
Plus 3/5 TAB.
right? Yeah.
Minus 1,000 pounds.
Right, so don't forget the applied weight of 1,000, this is in pounds in this one. Right, so I did put here that I did not have on Wednesday, that's the unit vector for the weight, negative K. If you do put it here, it's harder to forget to put it then in your equations. So this one, the Z, it's in the negative K, so that 1,000 is there. So counting these up, three unknowns, three equations, we at least know it's a solvable system. Going back to the find step that we did the other day, we were looking for well, I will put it here explicitly. We knew that the tension in AD was the weight, 1,000 pounds. But more importantly, more interestingly, are these three equations here for the three remaining unknowns that we wanted, those two remaining tensions and FAO. So as far as we know it's a solvable system and we can get all the things we're interested in. So now we can move to the solve step. This one's not quite as nice as the other example we did on Wednesday, because if we look at how these, just about these three equations right now, the way that these three are structured, we have ACAO, AOAB, ACAB. So kind of every permutation of two we have here. We don't have that one nice equation that immediately gets us to a number as our answer. So solving this one is going to be just a little bit trickier, but we can do it by hand pretty easily. So what strategy can we take to solve this one by hand? Yeah. Right, so we can still use substitution. I'm actually going to do the opposite substitution, but the order doesn't really matter. You can use substitution multiple times is how we can do this. So in a 2x2 system, it's pretty straightforward. Get one in terms of the other, put it into your second equation, you're done. This one, you just have to do it multiple times, kind of do these cascading substitutions, and then work your way back up. So for example, I can rewrite, per your suggestion, I'm going to actually isolate TAC, just so it's how I did in my notes. So I'm going to rearrange this and find it for TAC. So it's going to be negative 13 over 5, 0.299 FAO. I didn't work out the decimals here, but you can do that. If I were solving this by hand, that's how I would do it. All right, so I have TAC in terms of FAO. And I'm going to do the same thing. It's really going to be problem dependent how you solve it. But I'm going to do the same thing and get TAB because I can also get that in terms of FAO. So FAO is on my right side, ACAB on my left. So the nice thing about this one, again, this isn't as tough as they could come for 3x3 systems, because we can make these two substitutions and now write the third equation using these two substitutions. So I have 12/13 times negative 13 over 5 times 0.299 FAO plus 3/5 times TAB, negative 5/4 times 0.954 FAO minus 1,000. So what I've done is now in 3.1, the only unknown I have now in this equation is FAO. So I can now use 3.1 to solve numerically for FAO. And it turns out to be a negative 698 pounds. So it's in compression. And AO it can be because it's a rod there, so it can be in tension or compression. So this is what I mean by this cascading substitution. We kind of make multiple substitutions, finally get a number, and now we want to work our way back up. So now that we finally have a number, I can put this number into equation 2.1 and get out that the tension in AB is 833 pounds. So it's in tension. Again, a quick check. It has to be in tension, so at least we can't rule out our answer yet. A lot of arrows here, but also put this negative 698 into equation 1.1 and get out that the tension in AC is 542 pounds. Also tension.